How's everybody doing? Can you hear me all right? Thumbs up. There might be some new folks on the call from previous classes, so hopefully be some old faces and new faces. Um, Music. So Dana, I just use the same music now. I got in trouble using other music. Not in trouble, but YouTube has copyright stuff, so if you're like using just music out of the blue, then without the rights, then you know not allowed to broadcast that. So I just use my own royalty-free music that I've purchased, and that's that. So that may be one of the only changes, but other than that, same kind of approach. So what we're going to talk about tonight is elephants. Who likes elephants? Everybody likes elephants, I think. I don't think anybody that doesn't like elephants. We're not really talking about elephants, but we're going to talk about something called peak nutrients and eutrophication. Bad for elephants, bad for humans. This is coming from a request from someone that said to talk about nutrients and runoff, stuff like that. So I'll try and make it a little more interesting than that, and I will, I promise you. So we're going to talk about that, and it's relating to a story that came out in the news quite recently. In fact, I think yesterday. Um, well, why? Like, I guess the first question always is with this stuff is why is it important? Why do we even need to care about this stuff? Well, I don't know if we necessarily do or we do not, but the news cares about this stuff. So here's an article. So as everybody knows, I will put through links as we go through, and these links are available in the notes that will be posted in the description of the video on YouTube when I'm done. So if you want them, you can get them there. So take a look at that article, and that is from yesterday's Guardian, or sorry, that's from the BBC. It was in the Guardian. Well, and what that shows there is a pretty shocking sight. And if you scroll down that page, you'll see about halfway down aerial photographs. I guess those are photos taken from a helicopter or something, or a plane of elephants that have literally dropped dead all over the place in Botswana. Did anybody hear about this story? Did you see this in the news? Anybody? I saw it, I think it was in the Globe. I think it was in the Globe. Just found out why. Well, we're going to talk about why, and this is what's interesting here with this situation. So that was the case. It was a huge mystery, actually, because this has been happening for a while. I think in the last few weeks or month even, and there's 330 elephants that have died. So it's not 1 or 2 or 10. There's 330 elephants that have just literally dropped dead in Botswana like that, sitting there. No sign of. They thought it would have been poachers, but their discs are intact, and just looks like they just fell over and died, which seems to be what happened. So kind of shocking. To give you some comfort, it doesn't take that's not that huge of a dent in the elephant population there. I mean, it's significant, but it's not massive. Like, it's not a massive die-off. It's not like there's 500 and like more than half of them are gone. Nonetheless, what's shocking about it is it happened. And we need to understand that, because this could quite easily happen elsewhere if we don't really understand what the source of this is, right? And this is our job as environmental professionals, to step into these situations and make some sense of it. So the question there is, what's really going on? What is the problem there? Well, it's a big problem, and it's been around for a long time. So if you read the headline in the news, even in that article I sent through, it says, climate change is causing elephants to die, or something like that. What does it say? Mystery elephant deaths caused by cyanide. Well, that's the right thing. In another one that I saw, if you look at the Guardian one, I believe, just let me take a look here. One sec. Guardian elephants. Okay. Yeah, one of them was referring to it being linked to climate change. I think it's actually in the globe. Um, just one second. I'll find that right one. Here we go. Yes, it is. It's the globe, actually. There we go. So it was the globe that stated that. Okay. So here's the Globe's article. Okay. If you look at that one there, you may not be able to see it if you don't have a subscription. So the Globe came out and said it's linked to climate change. Okay. So this is a big problem. If you look at that, and we'll get into this, that's been around for a long time. This isn't a new problem. This is like actually an old problem. But ultimately, what it boils down to here, really, nutrient management and nutrient transport. That is the problem here, and this is why those elephants have died. Okay, so we have to look at it for what it is first, and then we can start to kind of piece it together and figure out how do you deal with this kind of stuff if it's your job. Like imagine you got hired as the kind of environmental management consultant for the UN to go in and look at water quality for Botswana. You would have to deal with this. So first, what are nutrients? First thing we need to do with this stuff is look at the science first, like what is going on here. So the biophysical world is one of matter and life. And it's one where we as environmental professionals, it's why we study chemistry, biology, biochemistry, ecology, soil science, hydrology, etc. And basically, the environment out there in the world that we deal with is a bunch of life, matter, and energy doing crazy stuff. It's just working together. And our job is to decipher what is going on with this crazy stuff. So there's key nutrients that are used by plants and other biota to grow and flourish. And they're like the building blocks of food as well. So like you, and like without food, they will not flourish. So if we don't have these nutrients, things don't grow, right? For those that aren't familiar with this kind of stuff. I'll start with the basics and we'll get more advanced. So here's a good article here about this, about the fundamentals of this from National Geographic. The base building blocks of life essentially are a subset of the periodic table. Those are carbon, sulfur, oxygen, hydrogen, nitrogen, phosphorus, and potassium. And those are the key nutrients. There's micronutrients as well, but those are the key ones that are typically identified as major macronutrients. So, and when people are inorganic farming, which a lot of our agricultural production in the world is inorganic, meaning we use outside influences, supplement outside the agriculture with outside supplements. We often use fertilizers, and those fertilizers are comprised of nitrogen, phosphorus, and potassium, NPK. Has anybody ever dealt with that? NPK fertilizers, you see that? It's kind of standard stuff. Even at home, when we're putting fertilizer in for your plants, it will be some combination of nitrogen, phosphorus, and potassium. Okay, so here is a link to the EPA site on nutrient management, which cites how this is an issue, right? So for anybody that's, worked in the environment or studied the environmental field at all for any length of time, even over a year, you'll probably have touched on this subject. It's always one of the ones that we need to address. But we need to look at the environment as systems. Like we see in the news, these elephants dying, right? That's the first thing we see. Well, okay, wow, what's going on? It's tragic. Well, now we have to look at the systems that are at play, that are the dynamics of these systems and what is influencing them to cause this to happen. So we have to look at the environment as systems that are in dynamic motion. They're never static. There's always dynamic motion. Things are always moving, and nutrients aren't static, right? They can be like fixed in plants or people, but they're also part of dynamic processes that are always moving around, okay? And so these are known as biogeochemical cycles. So here's a good link that outlines what those are. If you haven't looked at biogeochemical cycles before, at least done it in a cursory manner, I really recommend taking some time to study them. Whatever you're doing, even if you're like, finished grad school and you're working now or whatever, take a bit of time to look at that. It's very, very important. And And the main ones that I'd suggest you look at are the carbon cycle, the nitrogen cycle, the phosphorus cycle, and the hydrogen cycle. And there are other ones as well, sulfur cycle, but for this kind of stuff, certainly agriculture, those are the main ones. You could say oxygen too, there's the oxygen cycle, but I mean, often that's not one that people refer to. And you need to know these as an environmental professional. So I'd recommend getting a book on this stuff. There's the generic stuff. If you're just starting out, go with something generic like this one here. Like this is your standard Earth System Science type of textbook. They tend to be expensive, but you can go and find them used for like 20 bucks. Like brand new, they're like 170 or crazy price. But you can find something like, there's so many of them, right? People, first year physical geography, everybody buys it, you know, it spends 170 bucks, and then 95% of the people sell them, so you get it for cheap. However, if you're really serious into this, or if you're working on things that are a little more high fidelity, like a little more focused and detailed, like when I was doing grad work on this stuff, on carbon cycling, you have to tune it up a bit. You need a little more detailed of a resource. So you either look at the literature, or I would recommend this book. This is the book on biogeochemistry. It's by a guy named Schlesinger, and it's a great book, and it's really well worth it. I think you can get that for cheap as well. So those are like the basics. You need to know what the cycles are, and you need to know what influences those cycles if you're really going to try and address something like this, like our challenge today, which is to figure out what the heck is going on with the elephants dropping dead. So the next question is, given our understanding of this stuff, is everything in balance? Right? Is everything working properly? Not necessarily. Sometimes it is, because nature works that way. Like the Gaia hypothesis, which we talked about before, right? Where everything is in sync, the world in harmonic balance. It's a nice idea, everything working symbiotically and together and in balance and regulating, self-regulating. And the Earth system does function as a self-regulating entity in many ways. For example, the energy balance and atmospheric constituents allow for the living conditions on the Earth, right? The actual composition of our atmosphere and the way that energy gets absorbed by our Earth system and then emitted from our Earth system is a perfect balance, which allows us to have a tolerable atmosphere, temperature-wise and so forth, and protect us from harmful radiation. However, even that gets out of balance, right? When we get too many greenhouse gases plugging that atmospheric window, which allows long-wave radiation to escape. Hence, climate change is a result of that. When you get this atmospheric window blocking long-wave radiation from escaping, it causes things to heat up because more energy is trapped. So atmospheric homeostasis is one sample that often used to describe why we have a stable atmosphere, right? However, the problem is there are some things that may disrupt the balance of these systems. And the most important issue that we're contending with today, and that is why we do a lot of the work that we do, is human activity. So as you're aware, and we talked about, I think it was last time, we're in an era that there is described widely as the Anthropocene, correct? So the Anthropocene is the era in which human beings are the most influential part of the Earth system, right? They are the things, it's human activity that is fundamentally shaping how the Earth works. Whereas, you know, in previous geological time eras or epochs, it was other things, right? So what would be something that was the most dominant force in previous geological epochs? What would be something that was kind of the thing that dictate what happened? Anybody? Starts with G. If you drive to Banff, you'll see. Glaciation, right? So the Pleistocene, I mean, that was all about glaciation. So we are in this era here, the Anthropocene, which is widely seen as the new era of human-dominated function on the Earth. But technically, we are still in the Holocene. Like if you want to look at the geomorphology of and geology of the Earth, we are in the Holocene. But the human impact on the Earth system has become such a dominant force of influence that this new era is dubbed as the Anthropocene. So it's evident in our climate system, because we can see what's happening now, and it's obviously something that we talk about a lot in the news, the climate emergency, for instance, but it's also relevant to other systems. And the one that I'm going to talk about tonight is nutrients. Nutrients, this is one no one talks about, which is bizarre if you ask me, but it's a big problem, right? So we first need to dictate, well, what is that system? Like the climate system, we know how that works, but there's nutrient movement. Like nutrients move around ecosystems. So you can see in this image here, this is how they go about moving around ecosystems, right? There's a flow. So if you go to that link, you'll see that it's a system, right? It's a cycle. And you can see this is for the phosphorus cycle, the P cycle. So you can see, okay, the weathering of phosphate rocks, you have geological uplift, plant cycling it, you have farming, runoff, you have leaching, phosphates in the soil, and then you have this kind of uptake, geological uptake. Now, those things operate at different time frames, obviously, right? The geological uplift takes a long time for it to occur. So we have to be careful about how we manage the use of nutrients and monitor their dynamics. When we look at something like this, when we're kind of environmental managers, we have to really understand what impact we're having when we start throwing down fertilizer, for example. And limnologists and oceanographers, but limnologists for freshwater ecosystems are very helpful for lakes because that's their thing. But is this cycle self-sustaining? So that's the question, right? And I'm going to get to the elephant thing. We'll get there, but I got to kind of chart our path there. Is it self-sustaining? Is it like our climate, for instance? Because the climate, under normal conditions, is some degree self-regulating. If you look at the energy balance, it's just our interference with it that is causing us problems. No, it's not. The cycle, this cycle, the phosphorus cycle, and the nitrogen cycle as well, is not self-sustaining. Particularly the way we're using it, because we have such high agricultural demands. So if you look at that image that I've put through there, and you see this kind of the farming and runoff and plants part of that, that is really causing this whole system to be a bit out of whack. Why? Because we have tremendous demand for food, right? We have very high agricultural demands, and we need to feed those crops with nutrients. We need to feed them. So it's a source of much scrutiny and research. There's a lot of work that goes on with respect to agricultural and nutrient uptake and what nutrients to apply when and how much and so forth and so on. The question is, though, are we optimizing the use of fertilizer? What are the impacts of fertilizer? And is the whole system sustainable? Right? Those are three of the questions that would typically be asked when we're looking at, an agricultural type of research. Okay, so this is a question. Here's an example of a paper that kind of follows that, right? So if you go to that link there, that paper is by Graham McDonald, a guy I studied with way back at McGill. And what they tried to look at there is, this is a great paper where they looked at how does this stuff all work together from a budgeting standpoint. So if you go to that paper and then you scroll down to, I think it's page, there we go. It's the 5th page, right? So on the 5th page there, you can see this figure. It's figure 1, okay? So what they've done there, and this is the objective of this paper, is for the US food production system, they've done an assessment, a model of the inputs and outputs of nutrients, phosphorus particularly, because phosphorus tends to be the one that's the most limiting in agriculture. And they've looked at that and they've estimated from real data, they've used real census data and so forth and other sources to look at the total amount of phosphorus fertilizer and mineral feed used domestically. So they estimate it to be 1,105 gigograms of phosphorus, okay? Some of that is coming in from crop and livestock imports and other residual imports, but really minor. The bulk of it is from fertilizer input. And then they've calculated what the outputs are, right? So if you look at this, this figure, you can see that there's a fair bit of accumulation of phosphorus in the soil. There's about 21% of it is exported as consumption. So for exports, they export whatever, corn or whatever agricultural products. So 21% goes out of the country. About 28% gets accumulated in the soils. There's some about 13% of farm losses. And then you have biofuel grains. So there's a lot that's, well, a fair bit, 10% that goes into biofuel. And then you have about 27% is net processing losses. And then you've got about 8% consumed in US diets. So if you look at that, you can see, and this is a great piece of analysis because you can look at the bulk amount of phosphorus that's put into the food production system in the United States and what portion of that actually goes into US domestic diets, which is quite small actually when you look at it. And there's pretty significant losses. You look at on-field, other farm losses, 13%, and net processing losses are 27%. So we're looking at a bit 40%, so almost half of the phosphorus that goes into that system is lost in one way, shape, or form, right? And there's pretty significant inefficiencies in how the agricultural system is working, which is quite interesting. Okay, so keeping that in mind, you can see that there's massive inputs that go into that, and there are pretty significant losses. We have to think about, though, in this, and if we look at the whole system of production, we have to think about the source of the nutrients, the losses, and what is required, right? So that figure just tells us a bit of the picture. It tells us how much is going in and where is all going out. It doesn't tell us how that then fits into the overall Earth system function at any scale, really. So the global picture is, and this is where it gets interesting. So this is now we're going to look at, okay, well, how does this fit within the global picture? And this is where it gets interesting. We have to think at different scales, right? So on a day-to-day basis, you know, if we're in, I don't know, Nelson or Fernie or wherever in BC, we might think about this on the watershed scale because we're seeing, like, you know, landscapes and impacts on water bodies and so forth. Whereas we also need to think about this on the global scale, okay? So if you look at the global scale, there's some pretty alarming issues that are coming up. So this link here is from the Stockholm Resilience website, and it's from a paper by Will Steffen et al., initially by Rockstrom in 2009. Will Steffen and others did that again in 2015. So who knows about this model, the planetary boundaries model? Who's seen this before? I'm sure some of you have seen it. I know some of you have seen it. Is anybody that hasn't seen that before? That kind of radial diagram that tells you how things are going. Yes, good. It's quite, I mean, it caught on, like it's pretty well established now in environmental research for sure. And it was big, it's a big deal in 2010, but kind of it's, you know, well understood now. So, but if you look at that though, what jumps out at you? What are the things that are problematic when you look at that? What are the areas that are most problematic? Because it's different slices of the Earth system, and it tells you if we're in a safe zone, if we should be worried, or if we have no worries, et cetera, et cetera. If you look at climate, so if you click on that diagram and you go to, they will give you the high resolution article there, you'll see on that climate change, although it's like every day we hear more and more on it, it's, you know, it's in an area of uncertainty with increasing risk. So it's a problem, but it's not beyond the zone of uncertainty, high risk. Getting there for sure. And this is 5 years old, so I'd say that would probably be further out there now, particularly with what's happening in the last year. Okay, I would say probably they would adjust that. But in the top left, you see biosphere integrity, and you see biological diversity and the ecosystem. This is the species density, so the extinction rate is part of that, and then biospheric integrity. So that's the extinction rate's quite high. That's a big concern. But the other thing that's excuse me, that's relevant to discussion is in the bottom. What does the bottom tell us? Look at the bottom part, the phosphorus cycle. Exactly. So Shane, MSY, no. That, I believe that's millions, I thought that was extinctions. Millions of species per year. I think that's extinctions. I believe I'm 90% it's millions of species per year, something like that. But look at that, right? So we have nitrogen cycle flow and the phosphorus cycle flow. Big problems there, right? When was the last time you picked up the Globe and Mail and there was an article on the front page that we have a nutrient emergency? Have you ever seen that in any newspaper? Has anybody ever seen that? No. And it's bizarre. It's really bizarre because it's very well understood in the scientific community that there's a big problem there. You know, it's, you look at something, this is heuristic, but look at the literature. You know, this has been, eutrophications are a problem for years. It's like you go to any research in any physical geography department in North America, and there'll be at least 20% of the people will be working on that stuff, 15% doing some sort of ag, nutrient, geochemical cycling type stuff. But you don't hear it. You don't hear much about it at all, which I find is quite strange. So that's why we're going to talk about it. So if you want to get into more detail along those lines, I would suggest you do, if you're really interested in this stuff, is go to the latest version of this paper, which is Stefan et al., Will Stefan et al., and go, sorry, wrong link. It's this one. It's this link, which is in Science. This is the article in Science. And if you're with Royal Roads, you can download it. And go to the section on biogeochemical flows. In that paper, there's different sections, land system change and so forth. Land system change is part of it, like that they're related very closely. But it's the biogeochemical flows section that will tell you a lot about how they came up with that. And the appendices as well, like how do they come up with that kind of ranking? What's the metrics that they use? Same with biodiversity. They'll tell you about the extinctions. That's why I know that it's extinctions per year that they're measuring there, because I've read that paper many times. So take a look at that. So if we look at this from a global standpoint and our system standpoint, we look at this and we say, is this imbalance in the Earth system operation? It is. There's an imbalance here. Is it sustainable, right? Can we keep on going like this? And that is, you know, that's our question. That's what we need to resolve, right? So peak P or N, peak phosphorus, peak nitrogen. Usually it's peak phosphorus. That's because phosphorus is the main nutrient that's usually the problem. Has anybody heard of this before? Peak. Have you heard of peak oil before? Yes. Okay. Peak oil is it's a theory, actually. I mean, there's merit to it, but it was developed in the 40s, I believe. And I don't know if I have a link to it. Yes, here we do. It originally, so this idea of peak whatever, in this case we're talking about peak phosphorus, it's much like the peak oil debate. The argument being that there's a fixed amount of a non-renewable resource and that we might run out of it. So peak oil, if we want to talk about peak oil, is the maximum rate of extraction before that resource starts to go into decline, before the extraction rate goes into decline. So here's a link if you're interested in that, in the whole peak oil thing, then you can go to this and read all about that. And it basically, you know, the arguments, they've had a lot of peak oil. I mean, the fear is that we'd run out of oil and so forth. And, you know, are we ever going to run out of oil? I doubt it. I think by the time we're already switching to other sources of energy. And the way the economics work is as resources become more scarce, they often become more expensive or harder to access and so forth. So Peak Oil talks in detail about that and tries to determine what variables will influence whether or not we're at the peak extraction rate. Usually it boils down to cost of extraction, the market demand for extraction, and then also government policies that influence extraction, right? So today, one thing that would influence the whole peak oil debate is the fact that we're having carbon taxation being implemented, cap and trade systems, and there's increasing pressure by governments to move to other sources of energy, right? So that's going to influence the whole peak oil curve. Now, peak phosphorus is a similar idea. The same logic applies, but it's applied to phosphorus, which is in phosphorus comes from phosphate rock. So it's a resource that is mined. Like we go and mine it and then grind it up and then turn it into fertilizer with adding stuff like nitrogen, phosphorus, or whatever we need to, and then it's sold and distributed to fields. So it's the same idea. It's not a renewable resource. It's not like it's like a tree or something like that. Once you use it, it is now in the system. Now it is recycled to some degree, but not readily like you see those systems diagrams that I showed you in the biogeochemical cycles. Often the recycling rate will be a very, very long time if you're relying on upwelling from the ocean, for instance. So this really caught traction, the phosphorus issue. You didn't hear much about it. Peak phosphorus, you heard peak oil a lot for the last 40 years, but peak phosphorus not so much. But in 2008, there was a price spike for phosphorus, which caused a lot of scrutiny into the economics and the supply-demand dynamics for phosphorus. And why do you think that is? It's because phosphorus is so critical to our food supply system. Like we need to have a good handle on the phosphorus supply if we're going to feed the world, basically. So there remains a significant amount of uncertainty with respect to the global supply of phosphorus. The estimates today range between 30 and 300 years. Like there's a big range of like where the actual, how much, like where is the peak for phosphorus extraction. And this paper is a good one. It's 2000 and when is it? I think it's 2010 or something. But if you look at that, this paper here, it's open source. They dig into it. They look into and analyze what are the dynamics and what influences. So clarifying the key issues of a vigorous debate about long-term phosphorus security. That's in 2011, right? So it's not that old. And it looks at the latest information and perspectives on global phosphorus scarcity, and then what implications that has for food security and so forth, right? Good little paper. So the fundamental notion behind the broad use of peak theory in the above cases is that the growing demand for the critical resource, whether it be oil or fertile soil, will outstrip economically available supply, annual production at some point, if left unchecked, despite some advances in technology and efficiency, meaning the demand for food will outstrip the supply of phosphorus based on our requirements. So we have a growing population. And clearly there's a lot of different things that are going to impact that: technology, change in diets, all that kind of stuff. So there are ways to model different types of interventions and their impact on the supply-demand dynamics. So here is one example of that. It's another paper. I'll put this through. So this is interesting. So this is a visual that will help you see how you could make some sense of that. So if you look at that, what you will see on this image, you'll see on the left-hand side the phosphorus. That's megatons per year of phosphorus. That's consumption. And then you have the year on the bottom, 1950 through 2070, and obviously 2070 is modeled going forward. And so you can see that, you know, they do this, and you do this with CO2 emissions as well. You have, here we go, it's grown and grown and grown. We had a dip here at some point, probably due to the economics, or I'm not sure what that was that caused that dip. And then it continues to climb, and then they have a business as usual curve, which means there's no changes, there's no policy changes. And then there's certain interventions on the right-hand side, sustainable measures, right? So they've broken this into two categories, phosphorus efficiency measures and phosphorus reuse and supply measures. So for instance, becoming more efficient with agriculture, like more precision in your agriculture, less use of fertilizers. That's going to knock it down a lot. Efficiency in the food chain, changing diets as well. That will change the amount of phosphorus used. Then reuse food in other ways, crop residues, human excretion. So that's using like manure and all that kind of sludge and so forth, and then phosphate rock cycling can bring that demand way down. Okay, so that's a really good way of looking at what are the interventions that can be done based on the patterns that we've seen and what we predict going forward for the use of phosphorus, right? Does that make sense in terms of how you'd visualize a problem like that? That's a very good way for policy people. You look at that and say, ah, okay, I can see how if I give a subsidy, right, to farmers to become more efficient in agriculture, I can help that curve down a bit. That's the thinking when you try and frame a problem like that. There's a really good paper called by Steve Pakala and Sokolow on climate wedges, where they did the same thing and they looked at greenhouse gas emissions, and then they determined what kind of policy interventions or changes, measures could be implemented to reduce greenhouse gas emissions. And those were things like renewable energy, shifting to natural gas as opposed to coal, and so forth and so on. That's a good paper. It's 2004. So with increased focus on efficiency and analysis, we can get a handle on this, it seems. We can get a handle on phosphorus availability and use. And the measures on the right-hand side of that visual, those are the things that you do, right? Those are your job to determine what those actions are and how to implement them. So that's kind of, your call to action for this specific problem, but this isn't the end of the story, right? That's looking at kind of a macro scale. So what about scale, the local scale, right? Because if we look at the planetary boundaries model, and then we look at something like that, we can say, okay, great, well, we can put in some national policies amongst all these different nations and hopefully get a handle on this. And that may be true, right? But that doesn't necessarily mean there's going to be less elephants dying. And I'll show you why. Even if we manage to get a handle on the global picture with phosphorus and nitrogen supply dynamics, there are still things at the local scale you need to pay attention to, like things like runoff, the efficiency, and the system dynamics. And there's many issues with runoff and phosphorus and nitrogen use. So if you look at that standard schematic, this one here that I showed you before, if we go back to this, here, this middle part here, farming and runoff, that part there, runoff, that's where a lot of problems occur, because that's where you get all of this runoff happening, and this goes into water bodies, right? All of the dissolved phosphates gets mobilized. If it's not absorbed by the crops, if it's over fertilized, then it gets washed into the water quite easily. It's very mobile. So the runoff is the problem, and if there's an excess of nitrogen and phosphorus supplied, it will run off, and it can accumulate in large concentrations in water bodies. Okay, and this process, if you haven't heard of this, can lead to eutrophication. Okay, has everybody heard or anybody heard of eutrophication before? Eutrophy, E-U, this is how you spell it. Okay, if you haven't, this is going to be, that's an important one. You will hear of it if you haven't heard of it. Okay, so in any given year, in most geography departments in the world, there's going to be at least one student who's going to be working on NP dynamics and eutrophication. Every thesis presentation, someone is doing it. It's so standard that it's expected to be one of the issues noted as an environmental problem. It just pops up all the time. It almost like I fall asleep when I hear them, usually, because it's like, here we go, eutrophication again. Anyway, nutrient levels can get so high in these water bodies, that runoff can become so high that this overabundance of nutrients overfeeds microorganisms in lakes. It's like they're getting gorged, like you're getting just like a flood of nutrients coming in, and it's a heyday for these small organisms. And so algae starts to become overabundant, and then it overconsumes the oxygen in the water body. This then impacts all of the other organisms that are in the water, fish, anything else that requires oxygen. And it's termed the biological oxygen demand. So the biological oxygen demand goes way up because there's so much demand for oxygen in that water. There's so many plants and organisms require it. So and this is what happens. This is what you get when this occurs, right? So look at that. That image there. That doesn't look like a nice place to go swimming, right? And that is the result. That's the end game of heavy nutrient loads that get transported into water bodies. And that could be a lake, or I'm not sure specifically where it is. But here's another image here of a lake. Okay, if you look at that one, that's a little more typical. You see that throughout BC and any given situation. Okay, and that is a eutrophied. So if you take that to the extreme, so if eutrophication goes to the extreme, it can pretty much kill life in a lake, because basically all of the oxygen is taken up. So nutrient management is a pretty serious issue from an environmental standpoint, and also a social and economic perspective. But we can also learn a lot from it from an analytical standpoint. And I know those of you that have done the grad courses, this is where you're probably thinking about the dynamics of these systems. So we can learn a lot about resilience and system dynamics here. Resilience and eutrophication. So this is one of those perfect problems for resilience thinking. Like, it's one of those problems that's really great for this type of thinking. Because we have a dynamic system with different critical variables that are changing, right? Dynamically. And in some cases, they may change beyond certain critical thresholds. And if they do, that can cause massive system change, right? So, I mean, you're doing a state change from a clear lake to a eutrophied lake. And the reason that has occurred is because you've gotten past a certain threshold of nitrogen or phosphorus in the water that leads it to that massive shift, right? And so this has been actually something that's been of great interest to a lot of the folks that work on stuff. It's a testable situation, caught the interest of scientists. So there was some early work that had been done. There's a guy named Steve Carpenter who did a lot of the work on this and still does, on lakes. So if you look at this link here, this is a paper. Yeah, I think it's a paper, a book. Yeah, it's Resilience and Restoration of Lakes, Steve Carpenter. That's from 1997. That's an old book, actually. But that's kind of talks about the role of these kind of resilient mechanisms, the pathological dynamics, alternative stable states, and those alternative states would be a eutrophied lake. Okay. Then later on, it gets more advanced or more refined, I guess you could say, in terms of the study that had been done, and we look at the regime shifts. So regime shifts in lake ecosystems, patterns and variations. So this is, again, another book that really goes into the details of stability, attempts to understand the variability of ecosystems and what contributes to stable conditions. And then they progressed with it even further and tried to get a more refined approach, or like get a little more precision with the analysis. And this paper here is about the automated data acquisition. So this is where this is a free, yeah, you can, I think this is open source, this one. Yeah, you can download the paper. Changes in ecosystem resilience detected in automated measures in automated measures of ecosystem metabolism during a whole lake manipulation. So what they did with this was they manipulated the lake, they caused it to cross a threshold, and then they monitored different variables with automated systems like sensors and stuff. A neat little paper. You can take a modeling approach to this, right? So if you want to simulate it by just using a software, so they develop a program, they can use Stella or something like that, and then develop a model, and then test your model. So this is a management of eutrophication for lakes subject to potentially irreversible change. And this is a modeling study where they looked at management procedures to study how certain changes in different inputs of phosphorus could or could not influence the lake dynamics, and also whether or not that's reversible or not. It's called hysteresis, which is a pretty neat idea. And then lastly, management solutions. So what do you do to manage these situations. And this last paper here from Ecology and Society, again, something you get access to, where they looked at managing the resilience of lakes, a multi-agent modeling approach, where they looked at different ways in which they can analyze how different things interact. And that's a pretty neat, and they use the panarchy model here for those that are familiar with it, where you have different kind of stages of either reorganization or destruction. So these situations are often more complicated than we think. That's the bottom line. Here's what I'm trying to get across, is we started with an image of elephants dying, right? And there's more to it than that often. It's not just about, like in the case of the global males, it may be linked to climate change, but usually we've got to really dig a bit deeper into it. So what about these elephants in Botswana? So these situations are often more complicated than we think, and we most certainly need some data, right? So if we look at this, this article again, this is going back to the Guardian, right? Now that we've just taken in like an hour or less, a look at what's going on in behind all this stuff. This is an article here about lethal algae blooms, an ecosystem out of balance. So this talks about toxic formations across the U.S. and the Baltic, and are a trend linked to the climate crisis and farming methods. Okay, so this is an article in the Guardian, so it's worth taking a look at. However, we need to dig further. So we have to worry about algal blooms. They're toxic and they have an impact on water quality, water availability, species health, and also and so forth and so on. But we need to understand the dynamics at play. So there's more emphasis on impact on harmful bacteria and cyanobacteria on elephants. So here is, so if we looked at this situation with these elephants again, now we look at it and say, okay, what is going on? Like, what is the real root of it? Like, the first thing we looked at was an article from the newspaper, but I found this paper, which again is free. You can take a look at it. You can download it. So take a look at this one. This is just published. It's 2020. So what they did, this is August 5th, so it was published just over a month ago. Mass die-off of African elephants in Botswana, pathogen, poison, or a perfect storm. So you can look through this article, and I took a quick scan through it, and they don't even mention climate change in this article. What they were trying to get at primarily, first and foremost, is what is the immediate cause of this, right? And the immediate cause appears to be harmful cyanobacteria, harmful algae. Okay, if you read through this, that's what they have determined. Number one, that's what's happening. But then also, we do also need to look at then the relationship between other things, like what is causing that then? Because it's an algal bloom that, if you can even see in those photos, it's obviously eutrophied water bodies. That's what's happening there. So what is happening then there? Is there somehow being an excess amount of nutrients being dumped into that water? Presumably, yes. Like there's got to be that happening somehow. In addition to that, we can also then start to look at, is there a connection between climate change, other variables, so temperature in this case, and whether or not there's these algal blooms are happening. And in fact, there is. So if you look at that article here, this is from Science, and it talks about the harmful algae and at the complex nexus of eutrophication and climate change. So if you read through that article, and you can get it as a and this is in the journal of harmful algae. Who knew there was a journal on harmful algae? You know, you learn anything every day. But if you look through that, they do cite that there's a bunch of things that are contributing to algal blooms. Nutrient presence is the big one. That's usually the dominant variable. And we look at this from a resilience standpoint. You've got to determine what are the different variables that are contributing to this. The dominant thing is NP ratios, like the amount of nitrogen and phosphorus in the water. However, also related to that are other biophysical conditions, one of which being temperature, as they note in that article. They say that with increased temperature, there's a higher propensity for algae to flourish, right? So it will contribute. But I'd be careful to say that it's climate change alone that is causing these things to happen, unless there's very clear proof. Because we need to look at these situations and say, and this one particularly, it says it looks at the relationship between increased temperature and certain organisms, metabolic processes, as well as the ecological stoichiometry. And the ecological stoichiometry is basically the balance of different amounts of nutrients, more or less, in the system, right? And that is the dominant thing, as we've seen. You know, it's a question of nutrients ultimately. So what do we do? Okay, we've kind of got a better handle on these elephants that are not doing so well. Now, if it's our job to manage this, we need to look at these problems at different scales. We need to look at the variables. Some of are faster and some are slower. Like if we need to actually do something about this, if it is climate change that's having a big impact, that's not something we can change tomorrow. Whereas nutrient input is something we can change tomorrow, or at least we can have a more immediate effect on it. Once we know the dynamics, we can try and manage the problem where we can. So we can reduce nutrient loading, for sure. Can we reduce climate forcing? Well, over the short term, probably not, but over the long term, hopefully we can. So it's this kind of analysis that is the foundation of good environmental management. It's the good type of analysis I want you to be able to do if you've worked with me or if you're working with me. And you need to break down these problems, defend your analysis, and propose effective solutions. Don't jump to conclusions simply based on dogma, okay? Because that's the mistake a lot of people are making these days. There we go. So that's the breakdown of peak nutrients eutrophication, bad for elephants, and it's bad for humans too. So it's an issue that will not go away, but hopefully now you're a little more aware of what the nuts and bolts are behind all this stuff. Any questions? All of these links and the content will be available for download from the description in the YouTube video. So don't worry about if you just don't worry about copying the stuff. It will be available to you if you want to download the PDF. Even in urban areas, wastewater treatment plants may or may not be removing the nitrogen and phosphorus in the effluent. Absolutely, good point. Yeah, this isn't a rural thing necessarily. Another one, septic tanks, right? Septic systems, waste disposal systems. There's tremendous amounts of nitrogen and phosphorus think about how much nitrogen and phosphorus is coming from human waste, aggregated human waste. So we need to manage that properly. And more we're going to see, feedlots, pig farms. Like pig farms there's tremendous amounts of manure that gets run off into water bodies. Often pig lots are near water bodies, right? So it applies to a lot of different circumstances, actually, nutrient management. Same with dumps, right? You may get a lot of organics in the dumps and all kinds of stuff. Questions? How about other wildlife species? Are the elephants more sensitive? Good question. I don't know. I didn't get that far. I would look at, it's a good question. I really don't know. I would look at this article. Just one sec. This one here. Which one is it? This one here. I would look at this to start. That one there, because the focus of that study was not as much on biophysical stuff as it was on the toxicology side of things. They really dig into it. So you could look at that. I bet you anything in that paper. I'm going to look at it right away, just to have a quick look. What I would do is I'd look at that paper. And I would. You can download it. Get the PDF. Boom. I'm just looking at it now. Okay, so it's by one. I've got this paper. I'm just going to go to the end. I'll look at the references. So they have a lot on here. There's beta toxin in African elephants. Diagnostically important is cyanobacteria. So this one here. So if I look at this second one, Beasley et al. We're looking at. It's 1989, diagnostic and clinically important aspect of cyanobacterial blue-green algae toxicosis. Toxicosis. That one would tell you, I think, I'm sure in that it's the Journal of Veterinary Diagnostic Investigation. I bet you they would have some studies that relate generically, not elephants alone, but look at the lethal characteristics of those toxins to animals in general, including elephants. But I mean, I would be surprised if they had elephants in that one. But they'd look at things in general. That would be a good one I'd look at. Yeah, this reference list has a good, here we go. Okay, eco-epidemiological and pathological features of wildlife mortality events related to cyanobacterial biointoxication in Kruger National Park, Journal of South African Veterinary Medicine. They would have other species in that one too, I'm sure. Have anthrax in sheep, there's another one there. So I think you would look at that. I mean, the elephants, again, when it comes down to assessing something like this, you need to look at the bioavailability of the toxin and then the lethal dose, right? Those are the two things. How available is something, and then what is the uptake of it? And if the elephant's just drinking a bit of it and the lethal dose is quite high, then they should be fine. Whereas if they're siphoning down that water, which they probably are, then they're getting a bunch of that toxin in their system. It's a good question. But that paper will tell you in detail. Anybody else? So for those in environmental management tools and sustainable development, the two active courses, this makes a lot of sense because we're dealing with a sustainable development issue, right? We've got climate change, we've got a biodiversity issue potentially threatened, we've got a nutrient management issue, it's an economic issue, right? Elephants dying could be bad for ecotourism. There's a lot of different imperatives that play there. Those in environmental management tools, the things that you'll look at in terms of environmental management systems and ways of analyzing this will allow you to address the problem and analyze it. So in both cases, there's different takeaways from this situation for what you're studying. So that is the news of the day. Hopefully it was interesting. If there's any other questions, if there's not any other questions, we're hitting an hour now, so that's a healthy time. Thanks for coming out that came. And it was recorded, so it will be posted on YouTube. I'll let you know when it's up. If you want to share it, feel free. Good to see the new faces out, or old faces.